Hiya! So in this video, we're going to look at the variance of a sum of many variables. This is kind of something we hadn't done. We kind of talked about this for expected value, but we haven't done this for variance. So the idea is that, like, for expected value, we always had this linearity condition, right? So if I had e of x1 plus x2, blah, 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 plus xn, remember how I can break this up into x1 plus e of x2 plus dot 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 plus e of xn. And for variance, the thing we kind of saw is that variance, I guess I can just go up and notice that for variance with two variables, we get an almost similar thing, right? We have the variance of two things is the variance of each thing, and then plus some correction term, which we call the covariance. Well, so then the question becomes, well, what happens if I have many things? What happens if I'm summing up n different variables? So here, this is var of x1 plus x2 all the way up to xn. So what is this equal to? Well, obviously, first thing we should expect is having all the vars. So I'm going to sum up over all the vars. So I have each one of them. But I'm also going to need all the covariances. So I'm going to need the sum of all the covariances between xj and xk, where j is less than k. Now this notation, I'm sure a lot of you have not seen before. Here. What this is saying is we're going to sum over every single pair jk where j is less than k. So for an example, let me do a quick example. If I do jk where n is equal to 3, n is equal to 3 of covariance xj, xk, what I would have is covariance of x1, x2, since 1 is less than 2. I would have plus covariance x1, x3, since 1 is less than 3. 1 is less than 3. I would have covariance of x2, x3, since 2 is less than 3, and that's it, right? I wouldn't have this one twice, right? So I can't do 2 less than 1. This is wrong. And so I don't have a second one of these. I don't have x1, x1 because 1 is not less than 1. So this is kind of how we're doing this. It should intuitively make a little sense. Basically, we sum over everything where j is less than k. So let's look at an example of this. And this is something we had looked at a while back ago. And this is the height of Canadians. We're not going to go as into detail as we did last time. But basically what we're going to look at is just the population, the height of the population in total. So we're going to let xi be the height of the ith person. So we take the whole population and we let xi be the height of the ith person out of 33, 38, whatever million people. We're going to let mu denote the average height. And we're going to let sigma denote the standard deviation of height. And we're going to let you, we should kind of remember this, that xn hat or xn bar is going to be equal to the average value. So x1 plus all the way up to xn divided by n. So this should give us our mu in essence. And in fact, we kind of actually get this. So we're going to calculate the expected value and standard deviation first off. If the n individuals are chosen with replacement, and also calculate them if the individual are chosen without replacement. So here's where things are going to get a little hairy potentially. So expected value for both cases is really easy. Both cases. The expected value of x1 plus xn, well, this is just equal to expected value of x1 plus the expected value of xn, right? So what this means is the expected value of x bar, n, is just equal to the expected value of x1 plus expected value of xn over n, right? Because this is x1 plus xn divided by n, right? This n we can pull out, and then the rest we can just expand by linearity. Each one of these has average value mu. So we have n times mu divided by n. So the average value is mu, which makes sense. If I take everyone's height, the average should be equal to the average. Makes sense. Standard deviation, this is where shit goes down, where it's a lot more complicated. Now, in the replacement case, it's really easy, right? If we're always replacing people, basically what that's telling me is every single thing is independent from before. This implies every xi is independent. And so what we have, in other words, covariance of xj, xk is equal to 0 for all j not equal to k. So what we have is the variance of x and bar is the variance of x1 plus xn over n. Here we can pull out the n. And remember what this is. This is just 1 over n squared of and then of our x1 all the way to xn. I'll just do this slowly. And then here, what we end up getting is, am I doing this? Yeah, this is okay. And then here we have 1 over n squared of var of x1. That was not an n squared. Var of x1 plus var of x2, etc. All the way up to var of xn. So what do we have? We have n of these, because they're all the same, divided by n squared. So this is just var of x1 over n. So that's what the variance is. What's the standard deviation of xn bar? Well, this is just, this is the square root of basically what we have, right? Of var of xn bar. So this is the square root of var of x1 divided by n. So what's the square root of x1? Well, this is, this top part is just the standard deviation of x1 over, and then over square root of n. Standard deviation of x1 is just mu, sigma. So we get sigma over square root of n, which we've seen these before. So this is numbers that you should be remembering that we've kind of seen this, right? These are the square root laws. Because they're independent, we're allowed to use this in this case. Now, what happens if they're not independent? So if they're not independent, so this is without replacement. Well, what we're going to notice is things get really horrible really, really quickly. Because what we have is the variance of x1 all the way up to xn. So let me first figure this out, and then we can do the n afterward, right? This is going to be equal to, well, the sum from before, xi, I is equal to 1 to n, plus 2 times the covariance of xj, xk, of j less than k. Now, each one of these we know these are equal to sigma. So what we have is n times sigma squared. Sorry, these are each sigma squared because we have to take the square root for standard deviation. And then here, what we have is, and this is probably going to be a little confusing as to why it's true. I'm not going to cover this, but it's basically true because of symmetry. This is equal to n 2 times n minus 1 over 2. And we can just look at just x1, x2. And this equality is by symmetry. So this, I guess I should do this. This to this is by symmetry. And this is because each pair is equal in distribution. So xj, xk are equal in distribution. And that's where this is kind of coming from. I'm not going to cover this. It's a little bit complicated. So for now, you can kind of just believe that this is true. And that'll be okay. I'm not going to ask a complicated question like this on the homework or the exam, so don't worry about it. For now, I'm just kind of sweeping things under the rug. But the thing is, this formula works for any sample size. And so what this works is, well, we can take n to be the size of the entire population. So if we take the size to be the entire population, what we know is that the variance has to be 0, right? There's got to be no variance because we're taking everyone. So what we have is, if we let n be the whole population, population, then what we have is the variance of x1 all the way up to x capital N is equal to 0. And what this implies is that we have this kind of formula from up above. We have 0 is equal to n, so capital N sigma squared, plus, well, the 2's kind of cancel, and we'll have n times n minus 1. And then whatever this covariance of x1, x2 is. Well, now we can actually solve with this x1, x2, right? We can just move this to the other side. So we get minus n sigma squared is equal to n times n minus 1, covariance of x1, x2. And then that implies that the covariance of x1, x2 is equal to minus n sigma squared over n times n minus 1. We can cancel these n's. So we get minus sigma squared over n minus 1. Well, okay, so how does that actually help us? Do we actually get an answer? And this actually turns out to help us dramatically. So this, let's go back to trying to figure out the standard deviation. This, if we kind of recall, is going to be the variance of x1 all the way up to xn divided by the square root of n. This we just saw a few minutes ago. This variance from above, well, what did we say this is equal to? This is equal to n sigma squared plus n times n minus 1 times this covariance. And this covariance we just said is equal to minus sigma squared over n minus 1. So this is definitely a little complicated as an example, but it'll show you like the kind of cool things here. So this should be this squared, sorry. Wait, am I missing? Should this be n? Yeah, this should be n on the bottom, huh? Oh, because we can't do that trick from before because we don't have the variance. Never mind. So the problem here is I can't really pull this out yet. That was my fault. But what we do know is this. So here we can use the fact that the standard deviation of x1 all the way up to xn of n, we can pull this n out and do 1 over n standard deviation of x1 all the way up to xn. So that's the thing we can do. So here we'll have to divide by n. So we can't use the variance like we did in the last one. We have to use this from standard deviation examples. So from here, so we just have an n on the bottom. This is a side note for that mistake. So this is equal to, let's see, so I can pull out a square root of n divided by n, and then I have a sigma, so I can pull out a sigma squared too, sigma squared, and we get 1 plus n minus 1, or I guess minus, I can bring the minus here, divided by n minus 1. So we get sigma over square root of n times the square root of 1 minus n minus 1 over n minus 1. And I guess this is where I leave it. So this might look a little nasty, but this is why sampling without replacement is just always a little nastier. It's not very fun. Notice how it's a much more complicated problem. But it's not a thing you can't do. It's definitely something you can do, right? These are all tools that you've learned in this class so far. So yeah, so I'll stop this video here. I'm assuming there'll be some questions for this, and we'll get into that when class happens next week. But yeah, so we'll stop here. In the next video, we'll see the last section, and that'll be probably a quicker video. There won't be an example or anything. So yeah, so I will see you in the next video. See you then. Bye.